Good afternoon, and welcome again to the European and Associative Algebra Seminar. It's a real pleasure to introduce the speaker of today, Andrea Albano from the University of Salento. We talk about set-theoretic solutions of the Yang Baxter equation and di-skew braces. Please, Andrea.
Okay, so good afternoon, everybody. Let me start by first thanking the organizers for giving me the possibility to be here and present some of my results. Of course, let me also thank the organizers to organize this platform to let PhD students and young researchers to present and share their ideas and their results and their works. It is of the utmost importance to me. So today we will see the talk will be based on some results obtained in a joint work with my PhD supervisor, Paola Stefanelli, and will be basically divided in three parts. In the first part, I will briefly talk about associative d-algebras. In the second part, I will specifically talk about generalized digroups, which is an interesting structure that arose with the aim of splitting the notion of groups. In the third part, we will see how with generalized digroups we can produce non-degenerate solutions to the set-theoretic Yang Baxter equation. So let us start from the beginning. A D semigroup is a set D together with two associative operations, together with two associative products that satisfy the equations that you can see on screen. Now, the idea here is that these semigroups should, in a sense, furnish a split notion of semigroups. And indeed, the identities that you can see do exactly this thing. Now, a bar unit is an element E in D, in a D semigroup, with the property that it behaves as a unit element on the bar side of both operations. The set of all bar units is called the halo of D, and when the semigroup is furnished as non-empty halo, then we say that the semigroup is a d-monoid. So a d-monoid, briefly, is a semigroup with non-empty halo. Of course, all of these notions can be transported in any monoidal category, and this definition here is just the same thing in the category of sets with its usual monoidal structure. But of course, we can do the same thing, for example, in the category of vector spaces over some field. And it was exactly what Jean-Louis Loday did in 2001 when he introduced the notion of d-algebras, associative d-algebras. Now, to get an example, just to get a flavor of what we are working with, consider a monoid D together with M together with a bimodule D and an equivariant map F from D to M. Then we can define two binary operations, as you can see on screen, that produce a dimonoid in this way. Actually, it can be proven that all the semigroups, all demonoids can be constructed in such a way up to isomorphism, but it's not important for now. Now, why should we even bother with pairs of associative operations, of course, you may ask? And the reason is quite interesting, and it could actually be the basis of basically another talk for another hour. So before doing that, before justifying that, let me first recall what a Leibniz algebra is. A left Leibniz algebra is a vector space G, frac G, endowed with a bilinear bracket such that it satisfies the equation on screen. Now, as you can already notice, the identity that you can see on screen simply states the fact that the left multiplication operator with respect of the bracket is a derivation of the algebra itself. Hence, the name is a left derivation of the algebra itself, hence the name left. Of course, there is a dual notion of right Leibniz algebras, but the two categories, the two theories are basically equivalent. Leibniz algebras are interesting because they can be thought as a non-commutative versions of Lie algebras, or better, Lie algebras can be interpreted as an alternating subclass, an alternating version of Leibniz algebras. And of course, given the usual classic relationship between Lie algebras and associative algebras, and of course, many other ingredients that I'm not talking about here, one can wonder, what about Leibniz algebras? Well, what Jean-Louis Loday was interested into is basically transporting what I was saying before in the realm of Leibniz algebras. For example, if we take an associative D-algebra, as I was saying at the beginning, which is just a D-semigroup in the category of vector spaces over some field F, and if we define a bracket in this way, then it's not very difficult to show that what you get is a Leibniz algebra, is a left Leibniz algebra. And moreover, the rule that assigns to each associative D-algebra its associated Leibniz algebra in this way is functorial and is basically a side of an adjoint pair. Of course, here there is a lot going on, of which I'm not talking about now. And it could be really interesting to see how this all plays along. For example, one can ask, what is the role of groups in this case? How do they fit into this framework? Well, this is exactly what Loday asked back in 1993 when he was interested in stating the so-called coquecigrue problem. I will not delve much more deeper than this into the details of this problem, but it can be basically stated as, given the usual classic Cartan-Lie theorem between Lie algebras and Lie groups, what can be said about Leibniz algebras? Is there a so-called coquecigrue structure that would integrate Leibniz algebras under some hypothesis, under some conditions? And it is actually an open problem, even though in the years, many partial approaches have been proposed. For example, Michael Kinyon in 2007 proposed the idea, used the idea of Digroups to integrate the so-called class of split Leibniz algebras. A bit more on this later. Based on ideas from Kinyon, Kovets, I'm sorry if I'm mispronouncing it, in 2013, provides a local integration procedure for Leibniz algebras, which, by the way, in detail has been recently proved to be global in the case of two-step nilpotent Leibniz algebras, for example. This is a result, if I guess correctly, from La Rosa and Mancini from 2022, so quite recent. So apart these, there are also some results from Mostovoy and Bordeman and Weigmann, which are a bit different, but I will not delve deeper in these. So I will basically, this talk will be basically based on the idea of Digroups that came from Kinyon and other mathematicians back then. So let me well define what I'm talking about. A generalized digroup, or a digroup, put simply put in the next few minutes, is a D-semigroup So a set D together with two associative operations that satisfy the three identities that we have seen before, such that there exists at least a bar unit, and such that for each fixed bar unit and for all elements X in the set D, there exists a unique pair of unilateral inverses XIE, XJE, in the sense that they satisfy the identities that you can see on screen. Actually, I am not citing it right now, but basically the nomenclature, the way I'm writing this stuff is based on a paper from Smith. Now, as you can well guess, the unilateral inverses for each element do not necessarily have to coincide, of course. An example. Take a group G, your favorite group G, and consider a right action, C from G, or of G, I'm sorry, on a set E. Of course, the set must not be empty, so it should be not empty. If we define two operations, as you can see on screen, then the structure, the triple D left bar, right bar, this will be I will call the operations, will become a digroup, a generalized digroup in the definition, under the definition before, which in particular, from, let's say, an external point of view, we will denote in this way, so stressing the role of the map C. This is an interesting class of digroups, since it is quite easy to understand what are the idempotents of this structure, and this is basically the result. In particular, this structure, this digroup, will take the name of a hemi-semi direct product of the group G on the non-empty set E. The name, as I recall, if I'm not wrong, should basically come from a first version constructed for Leibniz algebras that appeared in a paper from Kinyon and Weinstein. Of course, feel free to correct me on this, since, of course, there can be previous occurrences of this construction. It is not, it may not be new, or it may not be new at this point. Now, let us work a bit with digroups. Let us do some structure theory for digroups. Let me first recall that given a semigroup, we can say that this semigroup is a right group if it is also a left quasigroup. So, put better, a right group is an associative left quasigroup, in the sense that left multiplication is bijective. The left multiplication operators are bijective. What can be proven is that if we start from a digroup, D left bar, right bar, then D left bar is a right group, D right bar is a left group, I'm sorry, that share the same idempotence. What I'm calling here idempotence is basically the halo of the digroup. So, each bar unit in the digroup is an idempotent with respect to both operations, of course, and conversely, each idempotent with respect to any operation here, left bar, right bar, is a bar unit. So the proof is quite elementary, and it simply amounts on proving that the left multiplication for the left bar operation and the right multiplication for the right bar operation are bijective. So I will just skim over this. I will skip this. Now, an important result on right groups, of course, there is a dual result, there is a dual notion for left groups, is that given any right group S, and once we fixed an element, an idempotence 0, then we can decompose the right group in this way. where G is a subgroup of S, E of S is the set of idempotents, and G and D of S only share the fixed idempotent, so the fixed 0. Of course, as I was saying before, there is a dual notion. There is a dual result for left groups. Now, we now know that in a digroup, we basically have a right group and a left group. So in this way, we know that, for example, if we want to fix on the left bar operation, but of course we can equivalently do the same thing on the other way, we know that any element can be decomposed in this way, can be written in this way, so that both operations can be characterized in this way. So if you recall from before, this is basically what a semi-direct product should be. Indeed, this is an old result from Kinyon that was slightly generalized by Salazar-Diaz et al. In 2016. Indeed, it can be proven that any digroup is of this form, in the sense that any digroup is isomorphic to a semi-direct product, where the action psi is just right conjugation from the groupal component on the idempotent set. Okay. Now, what we are going to do is use this decomposition, inspired by decomposition, determine a structure with the aim to uniformly produce non-degenerate solutions to the Yang Baxter equations. Of course, there have been mathematicians before me on this seminar that have already talked about the Yang Baxter equation. So for time's sake, I will just give the details that will interest this talk, so that will be important to understand what I want to share. Now, very briefly, given a vector space V and a linear endomorphism R on the tensor square of V, we say that R is a solution to the Yang Baxter equation, to the constant Yang Baxter equation, if it satisfies the equation on the screen. As you already may know, the Yang Baxter equation is one of the most fundamental identities in mathematical physics that arose in investigations of Yang and Baxter. Now, the Yang Baxter equation can be basically interpreted in any monoidal category. For example, the one in which we will be interested into today is the category of sets, together with its usual symmetric monoidal structure. In this sense, given a set D and a map R from D squared to D squared, we say that R is a solution to the set-theoretic Yang Baxter equation if it satisfies the set-theoretic version of the previous identity. Now, the advantage of working in set is that we have components. So given a solution R, a map R, we can introduce two families of maps, lambda A and rho B, so that we can write the solution in this way. So it makes sense to say that to state that the solution is left non-degenerate if all the lambda maps are bijective, right non-degenerate if all the rho maps are bijective, and non-degenerate if it is both left and right non-degenerate. Now, given two solutions, this definition will be important later on. Given two solutions, XR and YS, we can say that they are isomorphic, basically if we can transform one solution to the other after a rearrangement of the basis. Now, an important subclass of solutions, of set-theoretic solutions, is given by self-distributive structures. Indeed, if we take a map R, as before, from D squared to D squared, where D is just a set, equipped with a mag-map operation, so just a binary operation, assuming nothing else, and write and assume that the lambda maps are all the identities, And if we write the row maps in infix notation in this way, so using the magma operation, then it is quite easy to see, to verify that such a map is a solution, indeed, if and only if this magma satisfies this self-distributive identity. I should say a left self-distributive identity, since as in the case of left Leibniz algebras, we can easily understand a right version of what I'm talking here. But of course, the two theories as before are equivalent, so I will just use this left version. Okay, so there is this class of solutions that comes from what we call, what it's usually known as a shelf. More generally and specifically, given a set D together with such a binary operation, triangle, we say that the triangle is a shelf if and only if it satisfies this equation on screen in red. This structure arose in the investigations of Joyce and Matvev around knot theory, even though it can be traced back even before these works. Now, given a shelf, we can say that the triangle is a rack if and only if all left multiplication operators are bijective. In particular, we say that a rack is a quandle if it is also idempotent, in the sense that A, triangle A equals to A, for all elements A in D. Now, just for the sake of giving some examples of shelves, of racks in particular, and consequently of solutions in this way, which I've not, one of the most important one is the so-called conjugation quandle, defined on any group G, where the operation is this one, is right conjugation. There is another one also defined on any group G with a slight modification of the operation, defined this way. It is called the core quandle. Of course, I will not delve deep in the properties of these structures, even though they are very interesting. I'm sorry. Now, the first two are examples of quandles, so they are idempotent. The third one, which again is defined on a group G once we fix an element X, is an example of a rack which has no idempotence unless in some uninteresting cases, unless X, the element which you fix, is central, of course. There is an error here, or is the unit element of the group. Now, the importance of shelf structure, the importance of self-distributive structures is not only lies on the fact that they provide examples of solutions, important examples of solutions, but it also arises because it provides us with a general framework under which we can understand all left non-degenerate solutions. Of course, this is not the only framework that I could have used, that we could have used. It's just one very important framework that fits our motivations and our objective. So generally, given a shelf D, the triangle, we say that a map lambda from D to the automorphism group of the triangle is a twist if it satisfies the equation that you see on screen. The quite complex equation as you see on screen, but of course there's a twist. Since given a shelf and a map lambda, again from D to the automorphism group of the triangle, then the map R from D squared to D squared defined this way, where you can notice the first component to be what should be the twist, the second component, what should be the row map written in terms of the shelf structure and the wannabe twist. So given a shelf and such a map, it can be proven that such an R from d squared to d squared is a left non-degenerate solution if and only if lambda is a twist of or for the shelf that you start with. In particular, it can also be proven, this is very important, that all left non-degenerate solutions, so recall left non-degeneracy means that the lambda maps here are bijective. In particular, it can be proven that all left non-degenerate solutions can be obtained in this way. And this is very important, since following this framework, we can focus on the shelf structure, study its automorphism group. Of course, this is not an easy task. This is very, very far away from being easy. So do this and determine twists of the shelf. An important property I'm not mentioning here is that if you see a solution in this way, then the solution R is bijective, if and only if the shelf that you start with is a rack. So if and only if all left multiplication operator, the triangle, with respect to the triangle operation, are bijective. This will be important in just a moment. So how do digroups play a role here? Well, they are important because we can now focus on one particular shelf structure. It is in particular a rack structure. In detail, given a digroup, D left bar, right bar, there is a natural notion of conjugation, which, under this definition, provides us with a structure of a rack, which is called the conjugation rack of the digroup D. Now, here I'm skipping some details. For example, in the definition back then, I said that in a digroup, each element has different inverses, also depending on the bar unit. While here, there is no mention of the specific bar unit or on the specific side we are computing the inverse. The reason is that it's not important. It's not important because the inverse operation is taken on the bar side. And this is basically an elementary result in digroup theory that can be easily proven. Now, just for the sake of it, we know that all digroups can be, up to isomorphism, can be thought of as Amy semi-direct products in this way, where with respect to some right action of the groupal component on the idempotent component. In this way, the conjugation rack structure takes this very easy form, where we see that basically the right group action, the right groupal action, is again, simply in this way we can see it better, is again simply the conjugation from the groupal component on the idempotent component. In particular, it can be proven that it's not difficult to see this. It can be proven that this rack structure is a quandle if and only if the conjugation on the idempotent component is trivial. So if and only if A triangle E is always equal to E for all elements A acting on any idempotent E. Here, I'm sorry if I'm doing this, I'm basically using idempotent and bar unit in interchangeably. So pardon me for that. Okay, so what we are doing now is using this rack structure, and from this, determining twists of this structure to come up with interesting solutions. We do this by splitting the notion of skew braces. We have already encountered skew braces in this seminar, so I will just give some details about them. First things first. We say that a di-skew brace, so the prefix di here means just that we are thinking of it as a splitting of skew braces. So a di-skew brace is a set D equipped with 3 associative operations, where the first 2 gives you a digroup, as before. The circle operation gives you a right group structure. It's very important here to have a right group, as I will try to explain later, such that these 3 identities hold. Now, the first 2 identities you can guess are basically if you really know skew braces, they are basically a split version of the usual skew distributivity property of skew braces. The third one is a bit weird at first, even though it can be seen to be important, to be very important for the structure itself to produce solutions. I will try to explain this in a while. Now, again, I was talking about skew braces. And skew braces are the structures on which we took inspiration from to define the structure of these skew braces. In detail, a skew brace, now no split notion appears here. A skew brace is just a set with 2 group operations, plus and circle. Here we are not assuming that the plus operation is commutative. And as in the case of these skew braces, I'm sorry if I have not mentioned this, we are assuming precedence of the circle operation over the additive ones, where additive here for a skew brace means just the plus operation, while on the di-skew brace side means just the digroup operations. So I was saying a skew brace is a set with endowed with 2 group operations that satisfies the equation that you see on screen, this skew distributive property that combine the 2 group operations. Now, there is not time to delve deeper in skew braces since people before me have done the same thing here. I will mention 2 important but elementary examples of skew braces. So the first one is not difficult. All groups are basically examples of skew braces. The first triple here is usually called in the theory the trivial skew brace, while the second one is called the almost trivial one. Radical rings, where here plus is a commutative operation. Radical rings classically appeared as basically the first examples of braces. Here we are dropping the term skew since the plus operation is commutative. The first examples were indeed given by Wolfgang Rump in 2007, and the theory was later generalized under the non-commutative setting by Guarnieri and Tremaine in 2017. Now, it can be proven that skew braces produce important non-degenerate, hence bijective solutions. And this is exactly what we are trying to do now for these skew braces. First of all, before doing that, so it's not quite easy to come up with examples of di-skew braces because you can see this because we have to come up with 3 operations that satisfy these weird identities. Of course, it can be done. Here, I just want to provide an elementary class of examples. To do this, you can take a group, D, C dot, consider 3 idempotent endomorphisms, F, G, H, that share the same kernel, and define the 3 operations in this way. What you get is exactly a di-skew brace. Here, I'm sorry, there's an error. There's missing the circle operation. Now, this class of examples is not a coincidence and actually is a subclass of di-skew braces that can be achieved through the notion of compatible averaging operators, which we used based on results from a paper from Zhang and Gao quite recently in 2025. It is actually an ongoing work to understand better the structure of di-skew braces and studying its structure better that we can do now, at least in this talk. Now, let's speak of solutions. Take a di-skew brace, your favorite one, if you have one, and define the map, a map, lambda A, for all elements A in the set D in this way. Lambda A acts on B exactly as the lambda map from skew braces would if the left bar operation were the plus operation. So, of course, there are similarities here between the theories. If you let A vary, then we have a map, lambda, from the circle to the automorphism group of the digroup, of the additive structure. This map here can be proven to be a semigroup homomorphism. And the important thing here is this. So if you start from a di-skew brace, recall that we can consider the conjugation rack of the additive structure. Then what happens is that the lambda map here is actually a twist for the conjugation rack of the di-skew brace of the additive digroup. I'm sorry. And in particular, using the result we have seen before, the map R from the square to the squared, defined in this way, provides a non-degenerate and bijective solution to the Yang Baxter equation. The form of the solution is also similar to the form of solutions that come up from skew braces, even though there are some differences. And of course, you can see here, we can see the strong appearance of the additive structure, of this split additive structure here. Now, so where to go from here? We have shown, we have defined these skew braces. We have shown that starting from the additive structure and using its conjugation rack, we can produce non-degenerate solutions to the Yang Baxter equation. So what happens now is that it would be interesting to determine basically where do these solutions belong. So basically where in general we may find in the realm of solutions to the Yang Baxter equations. What I want to show now are 2 things. First, I would like to introduce a construction of solutions that is basically inspired by the structure of solutions coming from di-skew braces, and then show that these solutions belong to the first class, that they can be characterized in the way I am showing you now. Now, what I'm talking about here is a notion of semi-direct product of solutions. To understand better what I want to talk now, is important to give you some ingredients. So recall that the procedure that we are using here is start from a rack, actually from a shelf, but we will stick with rack structures, just because we from di-skew braces obtain bijective solutions. So if you want to recall what we are doing now, you can start from a rack and determine a twist of the rack to obtain solutions. This notion of semi-direct products basically wants to mimic what happens in more classical notions of semi-direct products, for example, as we have seen for Leibniz algebras or Digroups, where you have a starting structure, and starting from this structure and a notion of action, we can produce a new structure belonging to the same class on a Cartesian product. So to do this, start from a rack, X triangle. I'm sorry if I'm changing notation, by the way. And just for the sake of this definition, just for the sake of this notion, define an action of X triangle on a set E to be a map C from X to the symmetric group of E, satisfying the equation that you see on screen. Of course, this definition is also valid in the case of shelves, but we're sticking with racks for now. In this case, we can equivalently say that an action is basically a rack homomorphism from X triangle to the conjugation quandle of the symmetric group on E. An example, of course, we are not talking about the theory of the empty set. An example is just achieved by taking any rack and letting it act on itself by left multiplication. Now, this first ingredient is based on a similar notion from a paper from Kranz and Wegman, where they use this notion of action to construct the so-called semi-direct product of a rack and a non-empty set E on which the rack acts via an action psi. So, starting from a rack, X triangle, and considering an action psi, if you define an operation in this way, then you can endow the Cartesian product of X and E with a rack structure, where the operation is this triangle psi defined in this way. What we are doing now is taking inspiration from this definition and generalizing this to twists. So start with a rack equipped with a twist, lambda. Recall that a twist of a rack is just a map from X, where X is the rack, is the set where you are defining the rack, to the automorphism group of the rack itself. Recall also that given such a context where you have a rack and a twist, you can produce a solution, a left non-degenerate bijective, because we are considering a rack solution to the Yang Baxter equation, where the raw map is defined in this way, is constructed in this way. So what we are aiming here is this definition. Start from a rock, X triangle, equipped with a twist, lambda. We say that a hemi-semidirect pair of lambda of the twist with coefficients in a set E is a pair psi sigma, where psi is an action of the rack on the set E. Sigma is a map from X to the symmetric group of E that satisfies the equations that you can see on screen. Let me just note that the first one of these equations can remind you of the first braided entity that you can get once you develop the braided entity indeed in components in the set-theoretic context, in the set-theoretic case. Now, what happens is that if you have a rack equipped again with a twist, and if you consider a hemi-semidirect product with coefficients in E, in a set E, then you can define a map lambda, capital lambda, from X times E to the automorphism group of the rack that we have seen before, where each map lambda XE is indeed an automorphism of this structure that acts on X times E in this way. Lambda XE acts on YF as in the first component as lambda XY, in the second component as sigma XF. So in a sense, when you have a hemi-semidirect pair of a twist lambda with coefficients in E, the first map psi of the pair is basically allows you to construct the hemi-semidirect product of the rack. While the second map sigma basically allows you to construct the twist on the first structure, on the former structure. Now, of course, this is a theorem. The fact that map lambda is a twist of this rack is a theorem, and it produces a solution. Such a twist produces a solution on the set X times E. So with an use of notation, we will write this solution in this way, just to stress the role of the two maps of the pair, psi and sigma, where here Rx is the solution that we obtain by the twist lambda on the initial rack X triangle, and Re is just an abuse of notation to denote the twist map on the set E. Indeed, as you can notice, the set E is just a set. It has no structure whatsoever, if not the one given by the pair psi sigma. So this notion of hemi-semidirect product of twist is actually an interpretation of, it's actually a subclass of a general notion of dynamical extension, which is based on an analogous notion for racks, which was given by Andruszkiewicz and Grania. Of course, there is an error here on the here. It's not this one. I'm sorry. Now, why am I introducing this? Is because this fact. Start from a di-skew brace. So again, recall, it's a die group, two associative operations, a right group, circle, that satisfy the three axioms from before. Recall that once we fix a zero element, an idempotent in ED, then we can write all elements A in this form, where G of A is the groupal component and E of A is the idempotent component. it's quite easy to obtain this decomposition, as we have seen before. G of A belongs to this subgroup. E of A belongs to the idempotent set again. Now, what happens is that we want to decompose in a way the solution that is attached to the di-skew brace, but there is a catch. The catch is that this G here is basically a subgroup if you equip it with the left bar operation. But it is not necessarily true that it is stable under the circle operation. So what we are doing here is to define a new circle operation, basically a translation, as you can see here, with respect to the fixed idempotent, such that we can define a new map, a new family of maps, phi G, in this way. So basically taking the lambda map of the di-skew brace and shifting it with respect to the idempotent. Recall that we have a right action, psi G, that acts on E from the right in this way. And set for all G, define for all G this map here, sigma G, which is basically the lambda action on the lambda action from the groupal component on the idempotent set. Now, what happens is that the triple G left bar black circle, so this is the new circle that we are considering, is a skew brace, is a sub-skew brace, whose lambda map is given by this shifted lambda map. Moreover, the pair psi sigma, where psi is the right conjugation from the groupal component on the idempotent set, sigma is basically the lambda action from the groupal component on the idempotent set. This pair is a hemi-semidirect pair of the twist phi with coefficients in the set of biunits, in the halo of the digroup, of the additive digroup. Moreover, what happens is that the solution attached to the di-skew brace is isomorphic to the hemi-semidirect product that comes from this hemi-semidirect pair. So in this way, understanding how the decomposition of the additive part behaves with respect to the solution attached to the di-skew brace, we are able to identify the class where the solution itself belongs to. And this class is indeed the one of hemi-semidirect products of solutions, at least with coefficients in a set without any other structure. So this is the end of my talk, and thank you for your attention. Grazie mille.
Thanks, Andrea, for this interesting talk. Are there any questions? I can't see any questions, any remarks, comments. Okay, if not, let's thank Andrea again. And we will resume next week at the next Monday at the usual time.
Thank you.
Thank you. Bye.
Bye-bye.